Justin Chang is a key member of our staff, and he is offered to do this presentation in lieu of Michael Klemm, who was not available. Michael Klemm is part of the OpenMP Standards Committee, uh, but this is going to go into some more of a deep dive into an actual application that's been ported with OpenMP uh, and OpenACC. Justin also leads our effort on the Lab Notes series on GPUOpen.com, and I strongly recommend that series. There's a whole bunch of short blogs on different technical aspects of programming for the AMD GPUs. And I'm quite pleased that Justin is going to be given the first part of this presentation, and I'll fill in for the last part for Leopold, who developed the materials, and I'll go ahead and give that part of the presentation. So with that, I'm going to go ahead and hand it over to Justin.
All right, thanks, Bob. Thanks, Bob, for the introduction. So, my name's Justin. I am currently a member of technical staff at AMD, working on the same team as Bob. And so today I'm going to give a directive-based GPU programming on AMD systems talk. And then, as Bob said, this is going to be a two-parter. But first of all, let me just recap what I mean by directive-based programming at a high level. So with OpenMP and OpenACC directives, developers can specify to the compiler code regions that need to be compiled for a host and for a device, typically CPU, GPU. So most of this is probably covered before earlier today. So like managing memory and data, where you can allocate memory on a hosted device, express parallelism and potentially mapping different work items to different threads. And then the important part is that compiler directives, they reduce the effort and development time for porting codes to highly parallel devices such as multi-core CPUs and GPUs. Okay, so in this talk, I'm going to demonstrate one, that OpenMP offloading is both compatible and competitive with our HIP API. Second, as Bob alluded to, I will be going over a ported application, namely MPAS Atmosphere, that can run on AMD discrete GPUs using OpenMP offloading. And the third, Bob is going to discuss a little bit about the heterogeneous memory management, which is ready to use on AMD systems. Okay, so here's the first part. So HIP and OpenMP is what I denote as hybrid programming, which here stands for the interaction of OpenMP with a lower level programming model like HIP. In other words, one can program with OpenMP in the style one might program with HIP. And so OpenMP supports several of these different interactions that one can use in their application. So you could either call low-level HIP kernels from the OpenMP application code. You could also call the HIP/Rock math libraries like RockBLAS, RockFFT, etc. from within OpenMP application code. You could also call OpenMP kernels from within low-level HIP application code. And I'm going to go over all three examples very shortly. Okay, so let's go over the first example. So suppose you have an OpenMP code and you want to go apply a HIP kernel. So let's go over the Saxby example. So here we have it. Here we have uh, a very short code. So we have a Pragma OpenMP target data map, which maps the variable X to the device. And then we have another map directive which maps the Y to the device. And then at the end of this region, we'll map the result of Y back to the host. And so this code here, this line here highlighted blue is going to be our HIP kernel. So first we allocate device memory as specified directions of transfer. And so within this blue line here, it points to a different function. So we have a void Saxby, which performs the Saxby operation here. And so what I have listed here is the pragma directives needed to enable OpenMP target offloading. Okay, so let's assume that this is an entirely OpenMP code. Let's assume that we want to implement the Saxby instead in a low-level language such as HIP. So here's how you would do it. So let me present here a HIP version of the Saxby kernel. So the top, so there's two parts here. There's the host invocation call, the voice Saxby underscore HIP, which reads in the size of the vector, the scalar value that you want to scale by, and as well as the two device arrays. And then we have the corresponding HIP kernel shown above. So these are device pointers, and we need a way to translate the host pointer that was mapped by OpenMP directives and to retrieve the associated device pointer. Okay, so let us now put this together. So when we put it together, we have now three functions here. We have the original OpenMP code, which initiates everything. We have the OpenMP target data map, which maps the X host data to the device, and then we first populate some values, and then we have a mapping table which has there's two addresses. There's for each variable. So for X, there's a host address, and then there is a device address. And now suppose we want to now invoke a HIP API from the OpenMP kernel. We have to use this use device pointer, which basically says that, okay, instead of, so now that we know that X has two addresses, one to the host, one to the device, we want to use the associated device address, which is highlighted in red in this underlying uh, function call. So this Saxby slash underscore HIP will now have a mapping table of the device addresses for X and Y. And so these pointers will then be read into this second function, void Saxby underscore HIP. So this float star X, float star Y, these contain the device pointer addresses of these arrays X and Y. So this is how you would put it together. And the key part is here is that at least this was true last year. I am unsure if it's true today, but the idea back then last year is that we would need to have two separate translation or compilation units. So the first two parts of the functions would have to exist in a separate HIP file, which has to be compiled with the HIP compiler. The second translation unit has to stand alone in a separate file, which needs to be compiled with either the Clang if you're using the AOMP compiler, or if you're using the Cray compiler, it has to be compiled with CC. Now, this is what we had to do last year. I'm not sure what the case is this year, but my suggestion is to continue to follow this practice of separating the OpenMP code from the HIP code exclusively, and to compile them separately with the appropriate compilation flags. Okay, here's another example. So this again is the OpenMP to HIP code, but this time I'm going to look at it from a Fortran perspective. So suppose you want a Fortran code, and in this Fortran code, you want to make a call to a HIP math library, which exists in C. So there's one option here. You could either write this as a standalone C wrapper, which will interface from this Fortran code to the C math libraries. So again, you would need two separate translation units. So you would need in this. Okay, let me see if I remember. So in this subroutine example, so we initiate all these different arrays. We populate the values. We initiate the rock blast handles, and then we again use the use device pointer in Fortran land, and then we would call the Fortran subroutine, which would then interface to the corresponding C uh, interface to the Rockbla's dgem invocation. So again, it needs to be separate translation units. You have this first unit, which is compiled in Fortran FTN, and then of course you have a second translation unit, which is compiled with HPC. So I'm just going to leave this code here. You can look at it later. I believe these slides will be available to all of you later, but and I'm also going to have some arrows just to kind of map everything together, so you have how the different subroutines point to different areas of within each translation unit. Okay, and so as I was alluding to, this is the first option. You could either create your own Fortran to HIP interface, or this is actually what AMD recommends now. We suggest that you guys can build HipFort and use their readily available Fortran to HIP interface. We find this to be much easier. The reason one may choose not to go this route is if you were using an old compiler, which because using this HipFort requires you to build HipFort with your Fortran compiler, and I personally had some issues with this a couple years ago, so which is why I went with creating my own Fortran to HIP interface. But I believe today support for HipFort with Cray FTN is a lot better, and we encourage people to use HipFort, which is supported by uh, our Rockham software ecosystem. All right, let me go over a third example. So now let's suppose you have a HIP code, a native HIP code, and you want to now invoke some OpenMP. So again, these are this basic HIP API. So you initialize the X and Y device pointers. You copy from the host to the device, and then we have a Saxby OpenMP invocation. And so here is just an example of how this would look. Again, separate compilation units. And then this example here, this is a little bit interesting. Now I'm going to show just a little bit more of what you can do as you invoke OpenMP target offloading. There are two key uh, directives you can use: number of threads as well as number of teams. So on MI100, the default configuration, at least with AOMP, is 256 threads by 480 teams. And so these are parameters we strongly encourage the community, the users, to fine tune if they want to get the best performance on their specific hardware. So this was a study that I had done a couple years ago. So with BabelStream. So this is on an MI100. So what I did here was I did a full comparison of our AOMP OpenMP offloading versus HIP for all kernels in both single and double precision. So all experiments were conducted on AOMP version 13.0-6, which is pretty old today, but nonetheless, the point of this experiment is to show that how when you as a user can optimize to fine tune, parameterize the number of threads or teams, you could actually get a pretty big performance boost, performance improvement. And so on the left hand side, I denote all the different uh, calls within all the different tests within BabelStream. And then I have the default threads teams configuration. And then this third column here, the OpenMP over HIP ratio, this just compares the performance of OpenMP versus what I get from the HIP backend. And so, of course, the higher the number, the better, at least from the OpenMP's perspective. And so we have found that just by tuning some of these uh, threads or teams, we could actually get a pretty significant boost, especially for some operations like the dot product, which at the time the HIP performance was not very good, but we were able to get the dot product of the OpenMP to be slightly more competitive. And so there are some cases where you do not need the default threads and teams configuration was optimal for MI100, but like this is now this is again data from 2 years ago on an MI250, 250X. It probably is very different. The threads, teams configuration that you need for each of these operations will probably be different. Nonetheless, we still encourage users that when they work on their applications, algorithms, that you consider playing around with the thread teams. Okay, so optimization for Babelstrom requires a different number of threads teams for each of the sub benchmarks. And I'm going to list a few references here. So AOMP is the AMD's open source Clang LLVM based compiler with support for OpenMP API. This is primarily for the C backend. And then as Bob alluded to in the last talk, like if we want to use the Fortran OpenMP offloading, we encourage folks to use the Siemens G4tran compiler. Now, I also listed the Babel stream as well as this is very important, the HipFort link, which contains readily available Fortran interfaces to HIP/ROCm libraries. Okay, here's the next part of this talk. So MPAS stands for the Model for Prediction Across Scales. It is a collaborative project for developing atmosphere, ocean, and other Earth system simulation components for use in anything climate or weather studies. And so it is a finite volume solver for non-hydrostatic atmospheric equations. It is written in Fortran. It uses directives for GPU acceleration. So it currently contains, or at the time it contained about 2.5K lines of ACC code. It's an ongoing effort still. AMD's approach is to import this to OpenMP directives. And so I have listed a couple links here, the MPAS GitHub IO website, which contains the documentation, as well as the link to the open source repository. And so MPAS, for those of you who are familiar, has many different models. There is the atmosphere, the ocean, and so I am focusing strictly on the atmospheric aspect. Okay, so the MPAS memory and data management. So all GPU buffers, they are allocated at the first time step and are reused for subsequent time steps. So updating the host from device occurs at the end of every time step. And so what I have here, I have some flow charts here. So if you look at the top left here, so this is the program, this is the MPAS driver. So when you run the time evolution, you would initiate the time step from just to evolve the simulation over X number of years, decades, and then within each time step, you would invoke this subroutine called MPAS pool get array GPUs, which would allocate the GPU arrays. And so if you look here, follow this red pointer, you would come to this MPAS pool get array, either a 2D or a 3D GPU. And so you would see here that in the MPAS uh, application, the developers have introduced the ACC directive, which is ACC enter data copy in. And so this enter data copy in, basically if this field array is not allocated on the GPU yet, it will create, allocate the memory on the device and copy the host component to the array. And so this will only happen on the first time step. Every subsequent time step that happens after that, this ACC directive will not do anything. And so as you evolve the time evolution, you just iterate, perform the computation for the finite volume non-hydrostatic equations, and then finally at the end of the simulation, you update the values to the host, and then you post-process. Okay, so So the idea is that we want to, okay, before we go back, the idea here is that in addition to the OpenACC backend, we would like to introduce an OpenMP target offloading backend. So how do we do this? So there are several types of code that exists throughout this application. So the existing OpenACC code, it serves as a rough guideline for our OpenMP offloading port. So the first step is to add existing OpenMP directives, the equivalent OpenACC directives, just side by side. So so I have a very simple example here, which has ACC parallel vector length 32 iterates over the loop gang clause, and then there's an inner two inner loops which iterate over the vector clauses. And so in this example here, we have introduced OpenMP target teams distribute, and then we also introduced the OpenMP parallel do SIMD. And so the target teams is what distribute would match anything that says the ACC loop gain. And then for anything that says ACC loop vector, we introduce the OMP parallel do SIMD. And so we introduce this into this first example. So this is what we call the initial port. But now let's note something here. So if you look at the code, if you look at these loop vectors, like we note that this inner loop invert levels it usually depends on the mesh. And so the invert levels in this particular benchmark is set to 26. So there are 26 levels in the vertical direction. And so this may be okay for a hardware with a shorter SID or warp length. So like on NVIDIA GPUs, a warp size of 32, 26 mostly fills that value. It fits pretty well. Whereas on the AMD GPUs, where our warp or rather wavefront size is 64, and so this 26 is actually not very efficient for our AMD GPUs. So I guess the question here is how do we ensure that most threads are doing useful work for these smaller meshes? And so one approach here could be to collapse the inner do loops. And so because we are working with an existing uh, OpenMP code, we want to make sure that any additions we make to code does not break the existing OpenACC backend. So we introduce macro definitions at the top of each source file to distinguish do loops from the ACC backend to the new OpenMP backend. And so the end goal here is to have one code with few adaptations for optimal use of different directive-based programming models. And so in this code here, now we've introduced two additional directives. So we have the GPU OMP, which denotes lines of code that are tied to the OpenMP offloading backend, and then the GPU ACC denotes the original OpenACC code that we do not want broken. And so what I have done here is that I have collapsed the loop. I have collapsed the do loops. So I have introduced the OpenMP target teams distribute collapse too. And so by rearranging some of the elements inside the the do loops, I am now able to get get functional correctness, and as I will show later in the slides, I will get a very good performance boost. So this is one way that you could apply OpenMP optimization on AMD GPUs for these small invert levels and for our hardware in general. Here's another example. So here's another OpenACC code. So the, uh, you have an ACC parallel vector length 64. You have a loop gang, and then you have the outer of do loop, and then you have all these inner do loops as well as the sequential regions of the code. And so I want to make two notes here. So one, the ACC cache is basically caches local arrays into shared memory. This is a OpenACC feature. There is no OpenMP equivalent at this time. And then, but we will still work our way around this. And then the other point I want to mention is that the collapsing the inner loops isn't always possible, because in the first example we demonstrated that we want to collapse loops as best as possible to utilize the AMD hardware as best as possible. But what we can do here is, let's first apply the direct initial port. So we apply the OpenMP target teams distribute with the same thread limit as stated up here. And then we also apply all the corresponding OpenMP parallel do SIMDs. And then for the ACC loop sequential, we don't do anything here, because if there is no OpenMP parallel, then these do loops by default will operate sequentially. And so we notice here that when we run this code, we notice that there is suboptimal performance of this particular loop, because when you look at the rock prop statistics, if you look at the register use, the register spills, we notice that there are significant spills, significant scratch usage. But so how do we so what can we do? So we notice that, as I said, collapsing the loops is not possible because of the reduction of the Q2 variable. But how can we rearrange the order of these parallel and sequential loops to hopefully improve performance and to reduce register spills? And so, yes, it is entirely possible. So again, we introduce uh, this OpenACC macro definition to preserve the original file, to preserve the original implementation. But for the OpenMP implementation, what we have done is we have rearranged the order of the sequential parallel do loops. And so notice now that we need multiple parallel loops, which will minimize the global memory reads and writes. And so by doing this pretty nifty rearrangement, we are able to altogether eliminate scratch use. And this is all with the Cray OpenMP offloading. Okay, so here is the benchmark that I was talking about. And so these are all the different uh, subroutines, all the different subroutines that use OpenMP offloading. And so in both of those examples, I have shown the initial port as well as the initial optimizations. And so by applying some of these optimizations, whether it's rearranging the for loops, whether it's applying just various changes to the code, we could get a pretty good like improvement in performance. And so overall, the overall GPU port, including the OpenACC backend, is still a work in progress. Even to this day, it is still a work in progress. Only a couple variables are copied back to the host currently in this example. So it's about only 7% of this entire time integration. And then, but the MPass updating GPU data back to the host, this will significantly increase as we introduce more physics and more variables to the code. And of course, HMM can play a pretty big role when such physics and variables are introduced. So that is the end of my part of the talk. So Bob, I'll just hand it over.
Okay. Yeah, you want to just keep showing the slides and I'll go through
Okay.
these. There's only a few here. So one of the things that is very interesting for developers using OpenMP is that on the MI200, the memory management feature allows the memory to be migrated uh, automatically between the CPU and the GPU. And it's a little tricky in the details, but that can be quite helpful when you're doing the development. And I'll show you why here on the next couple slides. So let's go ahead to the next one. So you have to use the right allocators. And in this case, you see we're using the new in C++. And then when you use the data, it's going to try to access it. It will get a page fault, and it will then migrate the data from the CPU to the GPU or vice versa. This means that in this example here, um, um, we have this directive here, but we don't see the map directive. So the map directive is not needed because we're going to use the automatic memory migration. That greatly simplifies the development of code. Um, and this is an approach you might take while you're doing initial ports of your code, because adding all that memory movement takes a considerable amount of time. And as Justin was showing in the code he was working on, you're usually moving through and doing one loop at a time, and to have to move the data movement directives as you do each loop takes more work, and it's error prone. So this can greatly facilitate the initial porting. You may want to leave it in there. It's and rely on the memory management features. Even once you get to the production stage of your application, there may be some overhead from this memory movement. In the long run, the compiler could actually generate the request for data earlier, but right now it basically does it when it encounters that the data is not available. And you might decide at the end of your port that you want to go ahead and insert the explicit data movement directives, and you might get higher performance from that. There's also some other ways you can do some performance optimizations by doing a prefetch of the data. We aren't going to go into that in this talk. Next slide. So if you look at with unified memory up at the top where we're using the memory movement, you can see that there's a lot less things going on. And with no unified memory, we see a lot more things happening. The data is being allocated and moved and deleted. So you can get some better or simpler coding if you use a unified memory. Next slide. So another feature that is worth using is to get memory alignment. So memory alignment can give you some performance boosts here. And right now the default is 16 bytes. Now that may vary depending on your system and compiler, but in this case it's 16 bytes. You can change the alignment with most allocations. I want to be careful with that. So if you're reallocating memory, it can be a little bit difficult to get the higher levels of memory alignment. So in this case, going from 16 bytes to 64 bytes for the alignment, that's just the start of the address that you're pointing to. So it doesn't really waste a lot of space, but it can really make the compiler more efficient. It doesn't have to do a partial transfer of that unaligned memory. So if you look at the bottom slide here, going from 16 to 64, we see with different OpenMP options, and even with HIP, you can see that we're getting a boost in the bandwidth performance of the system. So this is a general hint for GPU coding. You may find a little bit better performance if you use memory alignment. It's different with each compiler and with Fortran and C, but it can be worth the effort to get better to get 64 byte alignment instead of 16. Next slide.
One second. Just lost control. All right.
Ah, okay. So when you're doing unified shared memory, you need to put this pragma statement at the top of every file that has an OpenMP directive. That's required by the standard. Uh, so you can see here that it's inserted at the top of this routine. But if you're going to be using it, you need to make sure it's in every file. And that's a requirement by the standard. It's not a compiler specific thing. Next. And we have this is a slide is showing that you can do some prefetching, and you can also do there's some mem_advise calls. You can set different attributes for the memory. So we can prefetch the data uh, and get it before the compiler would or the runtime would detect that the memory's not there and move it automatically. You can prefetch it so that it's there when you hit that boot. Right now, that's still being optimized by our team, so performance should improve with time with that prefetch. Let's go to the next slide. Oh, and we'll be talking a lot more about memory management in talk tomorrow, the first talk, when we talk about the node memory model for the AMD GPUs. Next slide. So here's another example of the effect of this alignment. So here we're going to specify the alignment. You can do that with your compile flag, or you can use a call to set the attributes of the memory. So here again, we're looking at going from 16 to a new alignment of 256, and you can see that compared to this 733, we're almost doubling the performance here by using the new alignment. So that can be quite effective for your applications. Next slide. So we're just going to summarize here. And this is summarizing the first part of the presentation too. And this was a good example that Justin showed. The MPass codes are complex. They're tricky because of, some of the complex data management they're doing. I worked on the ocean version of it, trying to get it working with OpenACC, and Justin's work on the atmospheric model is quite impressive. And we can use the ROCm libraries, so you can use the BLAS, the FFT, the solvers, and we encourage that because that can make a big difference in your performance. You can tune the performance. I do want to caution, as Justin showed, it can improve performance, but as you go from version to version, it may change, and with different GPU hardware, such as MI100 versus MI250, you may find that you need to tune it again. The example here of the MPass code. You can see how you can mix OpenACC and OpenMP in a source code and use whichever one is more appropriate for the system you're running on. You can also, with some of the compilers, have part of the code in OpenACC and part in OpenMP and do a gradual conversion if you like. Not all the compilers is that feasible, but in some of them you can because they have the same back end. And you can see how we tuned the performance using teams and threads, specific teams and threads. There's other tuning you can do similar to that, or you could also look at the memory alignment for your allocations. And the heterogeneous memory management, where you're using managed memory, can be a significant performance productivity boost in developing code. And generally, that is the trend we're seeing across the HPC community, is moving to where the compiler can automatically do some of the things that we've been having to do with pragmas and directives. And I think that's it for this presentation. Okay, do we have any questions for Justin or for this last half of the presentation? Okay, so Michael's asking about synchronization, and that's really good. By default, I believe that at the end of an OpenMP region, a synchronization is inserted unless you tell it otherwise. So you have a way, I think there's a no wait clause. Is that correct, Justin?
Yes, there is a no wait clause if you want to run asynchronously.
Yeah. You do have to be careful though, because if you retrieve the data and you do not have the synchronization or the end of the region, you may not get a complete buffer back. So you have to be a little careful.